I'm Adam from RFOXiA, from our real lab. Today we're answering the question that nobody in the BLE industry wants to answer directly. Why does every module claim a different range, and why is every single one of those numbers misleading? Let's start with where the number comes from. When a manufacturer publishes a range figure for a BLE module, that number was almost always measured in what the RF industry calls a free space line of sight condition. 2 antennas, clear sky, no buildings, no people, no ground reflections, no interference. The transmitter at maximum allowed power, the receiver at the absolute edge of sensitivity. Perfect alignment. In that condition, yes, maybe you get 400 meters, maybe a kilometer if the chip is decent. That number goes on the datasheet, it goes on the box, it becomes the marketing claim, and then you take the module inside an office or mount it on a drone flying over a city or clip it to a robot moving through a warehouse and you get 30 meters. And you wonder what you did wrong. You did nothing wrong. The number was never real. Now there are a few specific things that are almost always left out of BLE range specifications, and each one of them alone would significantly change the result. Let me go through them. The first is transmit power. BLE operates in the 2.4 GHz ISM band. In most jurisdictions, the maximum allowed transmit power is plus 10 dBm. Some chips go higher with a power amplifier, legally, in certain configurations. When a datasheet claims maximum range, that number is virtually always at maximum transmit power. What they do not tell you is that operating at maximum power continuously drains your battery faster, generates heat, and in some configurations pushes against regional regulatory limits. The range number is real only at a setting most deployment conditions cannot sustain. The second is antenna gain, and this is where specifications get genuinely misleading. Most BLE modules use a chip antenna or a PCB trace antenna. These are compact, they are cheap, they are integrated, and they are directional, meaning the antenna does not radiate equally in all directions. It has a gain pattern. The range figure on the datasheet almost always corresponds to the direction of maximum antenna gain, which is typically broadside to the module. Rotate the module 90 degrees, mount it inside a metal enclosure, bend the antenna trace slightly with an incorrect PCB ground plane, the effective gain collapses and your range collapses with it. The datasheet does not tell you this, it gives you the peak number from the best possible orientation. The third is receiver sensitivity, and this is the one that matters most and the one that almost no BLE datasheet explains correctly. Receiver sensitivity is the minimum signal power level at which the radio can still successfully decode a packet. It is expressed in dBm, decibels relative to 1 milliwatt, and it is a negative number. The more negative, the weaker a signal the radio can still hear. A typical commodity BLE chip has a sensitivity of around -90 to -94 dBm. A well-designed module with a good RF front end can reach -104 dBm. That is not a small difference. Every 6 dB improvement in sensitivity approximately doubles the usable range. The difference between -94 and -104 is 10 dB, which corresponds to a range increase of roughly 3 times, all else being equal. And all else is never equal, which is why this number compounds with everything else on this list. The fourth is path loss modeling. The free space path loss equation, freeze transmission equation, if you want the textbook name, tells you how signal power falls off with distance in ideal conditions. It falls off as the square of distance. In real environments, it falls off faster. In indoor environments with walls and furniture and human bodies, the path loss exponent is typically between 2.5 and 4. In cluttered industrial environments, it can reach 5. This means that a module rated for 200 meters in free space might give you 40 meters indoors, not because the module is broken, but because the physics of signal propagation through materials is simply not what the datasheet assumed. The fifth is multipath interference. At 2.4 GHz, signals reflect off surfaces, walls, floors, metal objects, water, human tissue, as everything reflects. These reflections arrive at the receiver at slightly different times and slightly different phases than the direct signal. Sometimes they add constructively and you get a stronger signal than expected. More often in certain positions, they cancel partially or completely. This is called a dead zone or a fade. You can be standing 20 meters from a module in a direct line of sight and experience packet loss because a reflected signal from a wall behind you is arriving 180 degrees out of phase with the direct signal and partially cancelling it. This effect is position dependent. Move one step and it disappears. The datasheet range number was never measured in a reflective environment. The sixth is coexistence. BLE at 2.4 GHz shares the spectrum with Wi-Fi on channels 1, 6, and 11, which occupy the same frequency space as BLE channels 0 through 36. It shares spectrum with Zigbee, with microwave ovens, with cordless phones, with other BLE devices. In a dense urban environment or a crowded event space, the noise floor at 2.4 GHz is substantially higher than in the open field where the datasheet was written. A higher noise floor effectively reduces the sensitivity advantage of your radio. A module with minus 104 dBm sensitivity in a quiet environment might perform like a minus 94 dBm module in a noisy 2.4 GHz environment because the interference has raised the practical noise threshold. So why does this matter specifically for builders? It matters because if you design a system assuming the datasheet range number, you will under-engineer your link budget. You will deploy and discover the range is a fraction of what you expected. You will not know which of these 6 variables is the culprit because the datasheet did not tell you they existed. And you will either add expensive amplifiers as a patch or accept the reduced range or start over. The correct approach is to design from the link budget backward. Start with your required range. Add your expected path loss for the actual environment, not free space. Add a margin for interference, for antenna orientation variation, for multipath. That total loss budget tells you what combination of transmit power and receiver sensitivity you need. Then choose hardware. So that is why the numbers are wrong and why the receiver is the part that actually determines range. Now let me show you the hardware that was designed from that starting point. This is the result of designing from receiver sensitivity outward rather than from transmit power upward. 5 kilometers ground to ground, 20 kilometers man to drone on standard Bluetooth spectrum. No amplifier tricks, no regulatory gray areas. 2 megabits per second data rate, which means the link budget advantage of minus 104 dBm sensitivity is not spent just maintaining a weak connection. It is carrying real payload, drone telemetry, sensor streams, control data, all at full throughput. The STM32WB07CCV6 manages both the BLE stack and user application logic on the same core. This means the RF front end and your firmware share timing without an intermediary processor adding latency or link budget overhead. 57 by 47 millimeters. The 184 nanometer antenna is external, which means antenna orientation is a variable you can actually control, unlike integrated chip antennas where the radiation pattern is fixed to the board geometry. Because the link budget was solved at the module level, integrating GNSS, sensors and motor control does not require re-engineering the RF layer. The wireless performance is constant regardless of what else is connected to the ecosystem stack. The RFOXiA Connect app gives you a live view of what the link budget is actually delivering, map position, signal strength, sensor data, so you can verify real-world range against the physics, not against a datasheet claim. BLE chat is a direct consequence of minus 104 dBm sensitivity applied to mesh communication. Internet independent, no towers, text and voice between multi-nav Pro Plus users, and because the link is strong enough to function as infrastructure. Full open source access via SWD means you can instrument the radio layer directly. If you want to measure actual received signal strength and compare it to the theoretical link budget in your environment, the firmware gives you that access. The integrated RTC is a small detail that matters significantly in time-sensitive wireless applications. Synchronized timing across nodes is what separates a mesh network from a collection of modules that happen to share a frequency band enough. At RFOXiA, the reason the Multinav Pro Plus BLE module achieves 5 kilometers ground to ground and up to 20 kilometers man to drone is not because we shouted louder. We did not chase maximum transmit power. We focused on receiver sensitivity. The chip at the core of this module achieves minus 104 dBm sensitivity. Every additional 3 dB of sensitivity is roughly 40% more range at the same transmit power. That is where the real engineering is, not the number on the box, the physics underneath it.